Section 7.2 talks about orthogonal diagonalization. So, remember, diagonal matrix is a matrix that consists of entries across its diagonal and zeros everywhere else. And that's a very special matrix, because if you raise it to a power, you simply raise the diagonal entries to a power. Definition 1, if A and B are square matrices, then we say that B is orthogonally similar to A if there is an orthogonal matrix B such that B can be written as B transpose A, P transpose A, P. And I think you know where this is going to. If A is an n by n matrix with real entries, then these three are equivalent. A is symmetric. Remember symmetric? If you run across the diagonal, right, the entries have to match. A is orthogonally diagonalizable. A has an orthonormal set of n eigenvectors. Remember, orthogonal means perpendicular, but orthonormal means they are perpendicular and the magnitude of the columns and the rows are 1. This is theorem that I need for later on. A is a symmetric matrix with real entries, then the eigenvalues of A are all real numbers. That's the part I need. This part we're not going to need for this section. Eigenvectors from different eigenspaces are orthogonal. Well, we could check those easily. Let's start with number 2. It says, find the characteristic equation of the given symmetric equations, and then by inspection determine the dimensions of the eigenspace. Okay, well, let's see how this works. So to find the characteristic equation, I'm going to take the determinant of lambda I minus A and set it equal to 0. So I'm looking at lambda minus 1 for -2, for -2, lambda minus 1, a 2, a 2, and a lambda plus 2. What is that? That's a negative 16 and a minus 16 minus 4 times lambda minus 1 plus 4 times lambda minus 1 plus 16 lambda plus 2. Now we want, you know what, I think I know what I'm going to do. I'm going to shrink this just a bit. And put that up there. Now, here we're going to require a bit of algebra. And we're looking at lambda minus 1 squared, lambda plus 2 minus 32, minus 8 into lambda minus 1 minus 16 into lambda plus 2. Unfortunately, that doesn't work the way I liked. I was hoping this would have a lambda. Let me work that out on the side really quick. Lambda squared minus 2 lambda plus 1. I thought we would have to work them out because those are going to be lengthy like that. And that is going to be lambda cubed minus 2 lambda squared plus lambda plus 2 lambda squared minus 2 lambda minus 4 lambda plus 2 minus 64 minus 24 lambda. Oh, there's an 8. Oh, that's going to be lambda cubed and those cancel out. I have negative 24, negative 28 plus 27 lambda, and we have negative 64 plus 10 minus 54 equal to 0. Now comes the tricky part. I'm trying to factor lambda cubed plus 27 lambda minus 54 equal to 0. So I take factors of 54 divided by 3. So that is, okay, just making sure before I go on. That was a negative 27, right? That's negative 24, negative 28 plus 1. Okay. I was trying the numbers, it didn't work. So I look at the factors of 54. That's 1, 2, 5 plus 4 is 9. 3 divides that. 4 doesn't work. 5, no. 2 and 3, 6 works. 7, 8, 9. So 1 and 54, 2 and 27, 3 and 18, 6 and 9. Okay. Now plus or minus 1 doesn't work because that's going to give you a negative 27 minus 54. Negative 1 wouldn't work either because it'd be negative 1 plus 27. There's no way you could offset the 54. 2. 8 minus 54 plus 54 doesn't work. Negative 2. Negative 8 plus 54 minus 54 wouldn't work. 3. 27 minus 3 times 27 minus 54. Nope. Negative 3 will be negative 27 plus 3 of those minus 2 of those. That works. Negative 3 works. Negative 3 gives it a 0. So 1, 0, negative 27, and negative 54. Nine, negative 18, 54, and a 0. Now, I should try a 3 again. Whenever you get a factor that works, you try it one more time, or you could just say, look, that's lambda squared. It's quadratic. But if it wasn't quadratic, I would try that again. That is lambda minus 6 and 3, right? No, plus lambda minus 6, lambda plus 3. That should work. And times lambda plus 3. So we have lambda equal negative 3. And we have lambda equal 6. So these are the eigen values. Well, lambda equals 6 is going to be one-dimensional. And lambda equal negative 3, since it's multiplicity 2, that's going to be two-dimensional eigenspace. Right? Find the recursive equation by following by inspection. So they're not saying to find it, they say, what do you think it's going to be? Again, the work here is a bit more intense than what we are used to because you're dealing with a 3 by 3, but we want to get those out of the way really quick. The same deal here. I'm going to take the determinant of lambda I minus a equals 0, which means I'm looking at lambda minus 4, negative 2, negative 2. So a bit of algebra is required, and that is lambda minus 4 cubed plus 8 plus 8. Shouldn't have made a mistake. No, that's fine. Okay. Minus a negative 2 times lambda minus 4 squared. No. No. I should have put those in order, but I didn't. Those three, and those three. So that would be, let's see, 4 into lambda minus 2 plus 4 into lambda minus 4, not minus 2. And the green will be plus 4 into lambda minus 4. So altogether we're looking at lambda minus 4 cubed plus 16 minus 4, 8, 12 into lambda minus 4. I could factor this as it is, but that's going to confuse a lot of you. So I'm going to work this out. This is lambda cubed minus 3 times lambda squared times 4 plus 3 times lambda times f4 minus lambda 4 to the third, which is 64, plus 16 minus 12 lambda plus 48, and that is lambda cubed negative 12, negative 12, and this is 6 plus 48. 3, 12, and 16 times 3. Third, no. That's one of a kind. That's negative 12 lambda squared, and that's one of a kind. That's plus 36, 4 squared, 16, 30, oh, 36 minus 12 is, so we got that one right. That's 36 lambda. And what's left? 1648. Okay, there it is. I see the mistake. This right here gives a negative 8, not a positive 8. So that's negative 16. And that makes it 80, negative 80 plus 48, negative 32. And I want to know where does that equal 0. I can take lambda squared, that wouldn't factor. Okay, well, let's see what works. You know the first 3 integers are going to work. 1, 2, 3 doesn't work. 3 plus 2 is 5. So, okay, let's try 1. 36, 37 minus 48 is not going to work. Negative 1. So that is negative 1 minus 30, negative 37, and 30, 44 is not going to work. Does 2 work? Well, 2 is hard to see. Let's see if 2 works, if not negative 2. And we only want one solution because that's cubic. This will be quadratic. We could factor it. Again, 85% of the time the first 2 integers work, 95% of the time the first 3 integers work. This is lambda squared minus 10 lambda minus plus 16, so that's lambda minus 8 and 2. And there's another 2, so there it is. By inspection, lambda equal 2 will yield 2 dimensions. How do I put it? Two-dimensional eigenspace because it has a multiplicity of 2, and lambda equal 8 will be one-dimensional eigenspace. You could find them if you wish. Now we're going to do something slightly different. Find the matrix P. Well, we did that back in the days. What do we want? That is orthogonally diagonalizes A and determine P inverse A. So we're trying to find matrix B, where B is this. If you recall how we did this back in the days, these are the eigen vectors. This is the inverse of that, which is the transpose, and this is A, and that should give you the lambdas across the diagonal, which is a diagonal matrix. Let's see how this works. We're going to start with the determinant of lambda I minus A and set it equal to 0. That's going to yield 3 minus, no, lambda minus 3. Just forget that. Lambda minus 3 and a negative 1, negative 1 lambda minus 3. We want to set that equal to 0, right? That is lambda minus 3 squared minus 1 equal to 0. That's lambda minus 3, right? Difference of two squares. Lambda minus 3 minus 1 into lambda minus 3 plus 1 equal to 0. Lambda minus 4 into lambda minus 2 equals 0. So I have lambda equal 4 and lambda equal 2. If I take lambda equal 4 and solve the following augmented matrix, put a 4 in there. If you put a 4 in there, you're going to get 1, negative 1, negative 1, 4 minus 3 is 1, negative 1, negative 1. And obviously, if I take row 1 plus row 2 and row 2, that will yield a 1, negative 1, 0, 0, 0, 0. So here we could say x2 is free, and x1 is x2. So with lambda equal 4, we get 1, 1. And we're going to take lambda equal 2. And by doing that, 3 minus 2 is negative 1, negative 1, negative 1, negative 1, 0, 0. Obviously, if I take negative row 1 plus row 2 and row 2, x2 is free, and x1 is negative x2. These are the eigenvalues, these are the eigenvectors. It depends on how the order that I put P in. Well, I could say, look at, I want P to equal, and let's see how this plays. If I want the magnitude of this to be a 1, then I'm going to put 1 over radical 2, 1 over radical 2, because the magnitude of that is radical 2. Negative 1 over radical 2, 1 over radical 2, that's P. And what they want us to do, find a matrix P that is orthogonally diagonal, that orthogonally diagonalizes A, and determine P inverse AP. Okay, if I want to figure out P inverse, that's 1 divided by the determinant, or I could say that's the transpose from the previous section. And when they say determine P inverse A, P inverse is 1 over radical 2, negative 1 over radical 2, 1 over radical 2, 1 over radical 2. A was 3, 1, 1, 3, and P happened to be 1 over radical 2, negative 1 over radical 2, 1 over radical 2, and 1 over radical 2. And if I multiply those out, what should I get? Since I put them in that order, I should get 4002. Let's make sure we get that now. We could just say that. We're certain that's going to work, assuming we didn't take any mistakes. But to check the work again, to see how this works, well, let's see. That's going to be 3 radical 2. 3 over radical 2 plus 1 over radical 2, 4 over radical 2, and that's going to be 1 over radical, that's 4 over radical 2, and this is going to be negative 3 over radical 2 plus radical 2 is negative 2 over radical 2, and negative 1 over radical 2 plus 3, that is 2 over radical 2, multiplied by 1 over radical 2, negative 1 over radical 2, 1 over radical 2, and let's see how that works. And that will be 4 over 2 plus 4 over 2, right? 4 over 2 plus 4, that's 8 over 2, which is 4. Negative 4 over 2 plus 4 over 2 is 0. Negative 2 over 2, that's negative 1 plus 2 over 2, 1 is 0. And negative, a positive 2 over 2, which is 1, plus 1, that's the 2. And it checks. Hey, what do you know? Magic. No, it works. It always works. Now we have one more to go. We want to do the same thing on that. Now, of course, this will become very interesting when the eigenvalues are complex, but we don't do complex in this class. So again, we're going to take the determinant of lambda I minus a, set it equal to 0. That would mean I'm looking at lambda minus 6 at 2, and a lambda minus 3 equals 0. That would mean lambda minus 6 into lambda minus 3 minus 4 equals 0. Lambda squared minus 9 lambda plus 18 minus 4 is 14, if I'm not mistaken. And that factors 7 and 2. So I got lambda equal 2 and lambda equals 7. Now, if I apply this, lambda equal 2, well, let's see what we're solving. We're solving negative 4 to 2, and if I take negative 1, if I take twice row 2 plus row 1 in row 2, so twice of that will make it 4, negative 2. So x2 is 3, and x1 is negative, is 1 half x2. So with lambda equal 2, we're getting 2, 1. And with lambda equals 7, I'm looking at, let's see, 7, 1, 2, 2, 7, 4. Take negative twice row 1 plus row 2 in row 2. Negative 2 plus 2 is 0, negative 4, there you go. So here we have x2 is 3, and x1 is negative 2x2. Here they are. So if we want them to form, they are orthogonal, but to have this is 1 plus 4, 5. 1 over radical 5, 2 over radical 5. Right? We want to make them orthonormal. And this is also the same. But that one is negative 2 over radical 5 and 1 over radical 5. So we say, look, we know what P is. P is 1 over radical 5, 2 over radical 5, negative 2 over radical 5, and 1 over radical 5. And if we want to write P inverse AP, 6, negative 2, negative 2, 3. P is 1 over radical 5, negative 2 over radical 5, 2 over radical 5, and 1 over radical 5. And what do we know? If those are orthonormal, I could find the inverse really quick. And how so? I'll just take the transpose. And let me show you where I get that from. And you could do the product. And I know what this is going to equal. This is going to equal, since I put them in that order, that's going to equal 2007. Really quick. Was it in the previous section? Here we go. A square matrix has to be orthogonal if its transpose is the same as its inverse, right? And that's how I know that that's the transpose. And there it is. So the inverse and the transpose work out to be the same. And that's pretty much it for this section.